Expanding anything and without using identities and without differentiating, can you tell me the maximum possible value of this expression? If you can't, by the end of today's lecture, you'll be able to answer this mentally. Assalamu alaikum, everyone. Welcome back to Easy Taleem. I'm Irfan, and this is our 10th lecture in the A2 Pure Math P3 series for Cambridge 9709. Today, we are beginning what is probably one of the highest yield topics in the entire trigonometry chapter in A2, r cos theta minus alpha, or as we call it, r sine theta plus alpha. Okay, this is trigonometry part 2 of 3. Now, let's do a very quick recap. Last lecture on Monday, we didn't actually solve many equations. Instead, we built the foundations, right? And what did we do in those? We revised AS level trigonometry. We learned the reciprocal ratios. We did, which was 1 upon cos was sec, 1 upon sine was cosec, and 1 upon tan was cot. Secant, cosecant, and cotangent. We also derived the identities 1 plus tan square theta was equal to sec square theta, and 1 plus cot square theta was equivalent to cosec square theta, right? And then we developed the compound angle formula as well for sine. A plus and minus b was equivalent to sine A cos b plus and minus cos A sine b. We also did it for cosine of A plus and minus b, where the sign reverses in the expansion, which is cos A cos b minus plus. So if this is plus and minus, this is minus and plus. So plus here corresponds to negative here, and negative here corresponds to positive here. And this is sine A times sine b. And for tangent, this is, so tan A plus and minus b is equivalent to tan A plus and minus tan b in the numerator, and in the denominator the same cosine sine rule will follow, which is opposite. So 1 minus plus tan A times tan b. And then before extending them, so we did sine A plus b, cos A plus b, tan A plus b, and before extending them into the double angle identities, which was for sine 2A was 2 sine A cos A, right? Cos of 2A was equivalent to cos square A minus sine square A, and two more variations of it, which was 2 cos square A minus 1 and 1 minus 2 sine squared A, which we use very frequently in integration. And we also did tan of 2A, which was nothing but 2 tan A over 1 minus tan squared of A, right? Now, finally, we looked at examiner style proofs and exact value questions in our last lesson. Those identities were not the destinations, they were simply the tools. Today, we finally use those tools in our lecture, okay? Now, here's something interesting. Many students think today's topic is simply another formula to memorize, something like r cos theta minus alpha or r sine theta plus alpha. Now, you will be able to realize that this alpha, r, and alpha, they are the constants that we must find the values of, right? Now, but Cambridge is testing something much deeper rather than just you memorizing formulas. They want to know whether you recognize that two separate trigonometric terms can actually represent one single wave. That's the entire idea. Once you see that, everything else becomes much easier. Maximum values, minimum values, graph interpretation, trigonometric equations, even modeling questions later on. So, suppose I write 3 sine theta plus 4 cos theta. So a lot of you are going to see two functions, a sine function and a cosine function. Cambridge does not. Cambridge sees one shifted cosine curve or one shifted sine curve. That's a completely different way of thinking, right? And when I say that one simply shifted sine or a cosine curve, it's also the vertical stretch also matches with the other, right? We'll just get to it in a bit. So this is a completely different way of thinking. Today's lecture is really about changing the way you look at trigonometry. Now think about music. So this is the real life intuition of this. Imagine two people singing the same note. One starts just a little earlier, one starts a little later. What reaches your ears isn't two separate sounds. It gets fused into one combined wave that you hear, right? Exactly the same thing happens here. So this is a sine wave and a cosine wave, but they combine together, right, to form one new trigonometric wave called 3 sine theta plus 4 cos theta. But still, it is showing us two notes or two waves or two trigonometric functions, right? So we just need to shift them horizontally and stretch vertically. That's why we write everything in the form either r cos theta minus alpha or r sine theta plus alpha. So this is the vertical stretch and this is the shifted form here and here, right? And we'll see that which one we need to fuse this into, whether we need to fuse this into a cos or a sine, right? Now, what you guys are going to learn today is by the end of this chapter, you'll know where this formula, which is r equals to under root of a square plus b square, where a is this one, so this is a and this is b, where this comes from, instead of memorizing it. How to calculate this auxiliary angle? So this is the auxiliary angle alpha, okay? How to convert expressions into r cos theta minus alpha or r sine theta plus alpha, and how Cambridge immediately asks for the maximum and minimum value after this conversion. And finally, we'll solve a proper Cambridge past paper question exactly the way the examiner expects. This is also one of those chapters where students spend 20 minutes memorizing the formula only to forget whether it's plus alpha, minus alpha, cosine or sine during the exam. Today, we are not going to memorize anything. We're going to derive it. If you understand the derivation once, you'll never have to rely on memory again. So let's begin from absolute first principles, the way we always do in our lessons. No shortcuts, no magic formulae, no just remember this type of a thing. Let's build the auxiliary angle formula ourselves and see why Cambridge uses it in so many P3 questions. Now, so let me write down A cos theta plus b sine theta. Now this a is different from this alpha, okay? Now our goal is to turn this into one single cosine function, okay? I want to look at it like this, r cos theta plus or minus alpha, okay? So I want to see, so this is a and this is alpha, so there's a distinction. A is like this, alpha is like this. All right, so let's derive it ourselves. Now, so we have agreed on one thing. We want to replace this entire thing with r cos theta with a single cosine function, right? But the question is how? Not by magic, not by memorizing, but we have to derive it ourselves, right? So if we are given a cos theta plus b sine theta, now I can write this function beside it, r cos theta minus alpha. Now you guys must be thinking that if you already have a compound angle, why are you may wanna expand it, and you are absolutely right. So I will just like we would do in polynomial divisions, right? We are accustomed to making comparisons. Okay, so this is equivalent to r times, so let's expand it. So this is cos theta cos alpha, right, plus sine theta sine alpha. Okay, the sign changes when we are dealing with cos, right? If there is a cos, this in expansion, this sign changes into a plus. If there was a plus, this sign would change into a negative. Okay, now see, so if I multiply the entire bracket with this r, which is getting multiplied outside, so this becomes r cos alpha times cos theta plus r sine, okay, sorry, this is, okay, why did I write this? So this is sine theta sine, okay, so this is correct, sine theta, this is sine alpha. Okay, now, so r sine alpha times sine theta. Now, can you see something that we also have similar thing here, a cos theta plus b sine theta, right? So we are not proving that these are equal. This is simply our target. We are asking what must r and alpha be so that these two expressions, this expression and this expression, they become identical, right? So now you'll see why our Monday's lecture of compound angle was so important, right? So this cos theta minus alpha got expanded into this, then we multiplied this entire expansion with r. So now we have here cos theta and we have a cos theta here, so we can compare these two coefficients, which is r cos alpha and a, and we can compare r sin alpha and b, because here we have sin theta and sin theta, so we can make the comparison, right? So now if we so the only difference between these two sides is the coefficients of cos theta and sin theta, right? So now if two expressions are identical for every value of theta, what must happen? The coefficients must match. Therefore we will say that this pink one is, so a is equal to r cos alpha and this b equal to r sin alpha, right? So let's draw two boxes around them. Okay, these two equations are the entire chapter. Okay, now students often copy this without understanding, but let's suppose, so suppose you're given, okay, let me try to explain this to you using an example. Suppose you're given 5x plus 2 equal to 5x plus 7. Can this ever be true for any value of x? No, because constants don't match, because these are exactly the same. Therefore 2 can never be equal to 7, right? Likewise, if a cos theta, which we had above, a cos theta plus b sin theta was equivalent to r cos alpha cos theta plus r sin, I'm just copying it from above, r sin alpha sin theta, right? For every angle theta, then the cosine parts must match, right? So this must match this, because cos theta and cos theta are the same and they are both getting added, and this r sin theta alpha must equal b, because sin theta and sin theta are same and the plus sign between the two terms is exactly the same, right? So we can do the comparison perfectly, right? So this isn't a trick, it's simply coefficient comparison. Now comes the famous formula, which is r equals to under root a square plus b square, right? Now we are given a is equal to r cos alpha, b equals to r sin alpha. So if I write down, a, okay, let me write down here. So r is a is equal to r cos alpha, so I can also rewrite it as a square is equal to r square cos square alpha, right? And I was given b is equal to r sin alpha, and therefore if I square both the sides, I get b square is equal to r square sin square alpha, right? Now if I add both these sides, so this becomes a square plus b square is equal to r square, I can take it common, and I will have cos square alpha plus sin square alpha, right? Now what identity do we know here? So I'm pretty sure you guys, whoever is watching, you guys just blurted out that this must be equal to 1, and you are absolutely right. Therefore our r square is going to become a square plus b square for any value of alpha. Okay, now r is simply a square plus b square in the under root. Okay, and so this is a huge find. Okay, now we're not stopping at the algebra. Let's draw a right triangle. So this is a and this is b, right? So horizontal side is a, vertical side is b, and hypotenuse is capital R. Does this triangle remind you of anything? Of course, Pythagoras theorem, exactly. So therefore r is equal to under root of square root of a square plus b square isn't really a trigonometry formula. It's just Pythagoras r square equals to a square plus b square, wearing a trigonometry disguise here. Okay, that's why this value is often also called resultant. This is also called resultant, and this is the auxiliary angle. Right? So that's why it's the combined magnitude of the horizontal and vertical components. Okay, now how do we, okay, so we do have r, but you do realize that there was another angle alpha here, right? Now how do we find alpha? We know that a was equivalent to r cos alpha and b was equal to r sine alpha. Now I need to get rid of this r. How do I do that? Now if I divide sine by cos, I am going to get tan. So if I write down r sine alpha upon r cos alpha, so this is equivalent to b upon a, and I can cancel these two constants are in the numerator and denominator. So I'm having tan alpha is equal to b upon a, right? And therefore alpha becomes tan inverse of b upon a. Now see, for a cos theta plus b sine theta, if I'm converting this into r cos theta minus alpha, so if I have this cos written in the first place of the two terms, then I will have alpha is equal to tan inverse of b over a, where b is the coefficient of sine and r is equal to under root of a squared plus b squared. Okay, now if this was b sine theta plus a, or rather minus a cos theta, and you had to find out, now if you had to convert this into r cos theta minus alpha, okay, so first of all put this in the first place, so this becomes, and I will take minus common as well, so this becomes a cos theta minus b sine theta, and I'm dealing inside the square bracket right now only. So first of all this gets converted into r cos theta plus alpha now, okay, because this one is because this was negative, and since we are dealing with cosine, the sign changes, okay. So alpha is now going to become tan inverse of b upon a, where b is the coefficient of sine, and r is equal to under root of a square plus b square. And so now I can rewrite it as this r, which is under root a square plus b square, put it inside the bracket, and this is going to become cosine of, I will put a square bracket and then use the parenthesis for the argument of cosine theta plus alpha, and alpha was tan inverse of b upon a. Okay, this is how we would do it, and we are going to do quite a few variations of this. Now this is where students lose marks. Your calculator gives a principal angle, right? Principal angle only when you do tan inverse of b upon a, but Cambridge expects you to think about the correct quadrant when the coefficients are negative. Okay, and we dealt with one case here. The coefficient was negative here and we dealt with it, but there are quite a few cases, and okay, we'll practice that in the word examples shortly, and I will be revisiting quadrant choice after introducing negative coefficients. Now that we understand the derivation, remembering it becomes effortless. A is equal to r cos alpha, cosine goes with the cosine coefficient, b is equal to r sine alpha, sine goes with the sine coefficient when we were doing the comparison. No mnemonics, no guessing, just coefficient comparison, okay? So a cos theta, let's do a small summary. I hope you guys are taking notes as well, plus b sine theta is equal to r cos theta minus alpha, where r is equal to under root of a squared plus b squared, and alpha is equal to tan inverse of b upon a. We've done the hardest part of the chapter. Everything from this point onward is simply applying these three boxed results, okay? So this one, and one that we did above. Now let's use these results on actual Cambridge style expressions. We'll convert them into r cos theta minus alpha and r sine theta plus alpha, discuss sign conventions, and see how examiners expect the final answer to be presented. Okay, so now we've done mathematics. We've proved r is equal to square root of a square plus b square through Pythagoras theorem, and tan alpha is the ratio of b and a, where b is the coefficient of sine and a is the coefficient of cos. Now let's actually use them, because this is exactly where Cambridge starts asking marks. Okay, now let's express three what's happening, wait, let's reset this note shelf, wait a minute. Okay, let's use a new page. Now let me write down 3 sine, or rather 3 cos theta plus 4 sine theta and express it in the form r cos theta minus alpha. So first of all, a is 3, b is 4. Therefore, r is equal to 3 square plus 4 square under root is what? It's just 5. Okay. So it is going to be r cos theta minus, because there's a plus here and there's a plus here, so we will have a minus here, and alpha is going to become, so alpha is going to become tan inverse of coefficient of sine over coefficient of cos, which is 4 over 3, and that's approximately equal to 53.13. So alpha in degrees is 53.13. So I will write this down here. Okay, now this is very easy. So I can convert this two waves of sine, a cosine wave and a sine wave, into one vertically stretched and phase shifted cosine wave. Okay, now what is very important here is that you don't become a robot. Always verify. So let's expand mentally. So r cos theta cos 53.13 plus r sine theta sine 53.13. Now cos 53.13 is what? It is 3 upon 5. You can put it in your calculator. It's just the reverse of it. And this is r sine theta, and sine 53.13 is nothing but 4 upon 5. So you can put it in your calculator yourselves as well. So and this r is what? This r is, sorry, 5. So let me write down 5 everywhere. So this 5 cancels this cancels this. So we come back at 3 cos theta plus 4 sine theta, right? Always build the habit of checking. And can you see how we recovered the same form, 3 cos theta plus 4 sine theta from above, right? Now let's do another example. Let's make it slightly harder. So if you have 8 sine theta plus 15 cos theta, and you have to express it in the form r cos theta minus alpha. So now r is going to be 8 square plus 15 square under root is going to be 17, and alpha is now, let's see what alpha is going to become. I just explained it to you in a while back, that if you have to convert it into a cosine form, and cosine is in the second place, put it back in the first place, rearrange it. So this becomes 15 cos theta plus 8 sine theta, and now it's much easier for you to look at. Now alpha is nothing but tan inverse of 8 upon 15, which is approximately equal to, let me do it in the calculator, 28.07. so alpha is 28.07 degrees. So I can rewrite this as 17 cos, and because these both are plus, so I will have to put a minus here, alpha, the theta minus alpha, which is 28.07 degrees, right? Now this number 17 appears almost magically, but now you know exactly where it came from, which is Pythagoras theorem. 8 square plus 15 square inside the under root gave us this 17. Now remember the question I asked in the beginning, which was 8 sine theta plus 15 cos theta, and what is the maximum value of this, right? Without solving anything now. So you converted this into 17 cosine theta minus 28.07. So now cosine, what is the maximum value of cosine that it takes? It ranges between minus 1 and 1. So the maximum value that it takes is at 1, and when you multiply 1 with 17, you get the answer of 17. So that's the maximum value that this wave is going to take. Okay, one line, no calculus, no graph, nothing. This is why Cambridge teaches the auxiliary angle method. Now let's introduce r sine. Okay, in this auxiliary angle form, let's introduce, if you have to convert, so if I have r sine theta plus alpha, and if I expand it, so this becomes r sine theta cos alpha plus r cos theta sine alpha, right? Now if I compare this with a cos theta or a cos theta plus b sine theta, so this cos theta, so a is, let me highlight it so that you can identify. So this a is similar to r sine alpha, and this b is similar to r cosine of alpha. So let me write it down as such. So this becomes b is equal to r cos alpha. Sorry, did I write it down correctly? Okay, so sorry, I think I made a mistake here. Let me do it correctly. So we had to convert a cos theta plus b sine theta into this form. Okay, so first of all, I converted this into b sine theta plus a cos theta. The coefficients are different here, so b and a have changed places. So this is equivalent to r cos alpha, right? A is equal to r cos alpha. Oh, sorry. So this is a sine theta, sorry, plus b cos theta. Okay, never mind. So now when I expand it, what do I get? So I compare r. So let me shade it. So I compare r cos alpha with the coefficient of sine theta, which is a is equal to r cos alpha, and I compare the coefficient of cos theta, which is r sine alpha, with the coefficient of cos theta, which is b. So what do I get? I get the result, which is a is equal to r cos alpha, right? And r cos alpha, and b is equal to r sine alpha. Okay, exactly the same idea, only the expansion changed. Now this is one of the easiest place to lose marks. Students memorize that a is equal to r cos alpha, right? You memorize this from the cosine version and blindly use it everywhere. Don't do that. Always expand first, then compare coefficients. The mathematics tells you where everything belongs. So now let's say you have 5 sine theta plus 12 cos theta, and you have to convert it into an r sine form. So r sine, and because this is plus, the inside is going to retain the sine. Okay, so this is theta plus alpha. Now this is going to become r is nothing but square root of 5 square plus 12, which is 169, which is 13. So I will write it down. So 13 sine theta plus alpha. Now alpha is going to become ratio of 12 and 5. So tan inverse of coefficient of cos, which is 12, over coefficient of sine, which is 5. Okay, so tan inverse of 12 over 5, let me just quickly do it. 67.38. Okay, so this is 67.38. So I will put it here, 67.38 degrees. That's it. Now let's discuss something Cambridge absolutely loves. Suppose you are given, let me change color to make distinction. So let's say you're given 3 cos theta minus 4 sine theta. Now students are going to panic, but nothing changes. Now b is nothing but minus 4. Therefore tan alpha is negative 4 over 3. So tan alpha, if you're doing it into r cos theta minus alpha, so tan alpha is going to be negative 4 over 3, and alpha is going to be, so whenever tan is negative, it is in the second quadrant. So your calculator is going to give you, when you put this in your calculator, tan inverse of negative 4 upon 3, your calculator is going to give you negative 53.13. Okay, so this is perfectly acceptable. You just put it here and you get a plus sign. And what I told you, that whenever there is a minus here, you put a plus here, and then you use absolute value. You just use the coefficient. So if I were to do it, I would take r as 5, because 3 square plus 4 square inside the under root is 5, cos theta, and because there is a minus sign here, I will put a plus sign here, and tan inverse and alpha is going to become simply 4 upon 3, which is nothing but 53.13 positive, and I will put 53.13. Either way, it is absolutely right. Okay, what's important is that your expanded answer reproduces the original expression. So if you expand it, you're going to get a negative, which is going to reflect here. It is going to recover the original expression. Always verify by expanding. Never trust memory more than algebra. Okay. Now, I've marked enough Cambridge style questions to notice a pattern. Students rarely lose marks calculating the R, which is the resultant. They lose marks because they rush the signs: positive, negative, cosine, sine, plus alpha, minus alpha. Take 10 extra seconds, expand mentally, check the coefficients. That habit is worth far more than memorizing another shortcut. Now, let me give you a mini challenge here, okay? Pause this video, try this yourself. 7 cos theta plus 24 sine theta, and I want you to do it in the form r cos theta minus alpha and r sine theta plus alpha. I'm not giving go. So don't look ahead. Work it out. You'll discover a very familiar value of r. Okay, and I'm not going to solve it in this video. You are going to post your solutions in the comment section. Now, so we have now learned how to rewrite any expression into a single trigonometric function. But Cambridge almost never asks you to stop there. The very next sentence is usually hence find the maximum value or solve the equation. Let's see why rewriting into r cos theta minus alpha suddenly makes those questions almost effortless. Okay, so far we have learned how to rewrite a cos theta plus b sine theta as r cos theta minus alpha. Now here's the question, why did we bother? Was it simply to make the expression look prettier? Not at all. Cambridge doesn't teach this because it's elegant. It teaches this because it instantly solves questions that otherwise look difficult. Now, if I ask you 8 sine theta, let me change color because, okay. So 8 sine theta plus 15 cos theta. If I ask you without using calculus and without graphing, without using Desmos, can you tell me the maximum possible value of this? A lot of you will not be able to. But if I convert this into 17 cos theta minus 28.07, which you know how to convert this into, now what is the largest cosine value that this cosine function can ever take? Of course, you know that cosine for some value of theta is going to take a value 1, and 1 times 17 is going to give you the maximum value, and hence the minimum value is also going to be negative 1 times 17. So the range is going to be between negative 17 and 17. The amplitude now is 17. Now, because this is just phase shift of 28.07 degrees to the right, you know this transformation from functions. Now, there is one huge observation. This is probably the biggest reason that this topic was invented. Cambridge doesn't really care about writing r cos theta minus alpha or r sine theta plus alpha. They care about whether, not whether, but what this form immediately tells you, right? So if I write down r cos theta minus alpha, so if I write down with another color r cos theta minus alpha, so this shows the amplitude, right? This is the maximum value. The minimum value will be at r because there is no plus c, right? So I'm taking the liberty because a vertical shift changes the maximum and minimum value. By the way, the range is going to be 2r, the difference between the maximum and minimum, and the location of maximum, because this r is going to appear where this cosine function is 1, right? So this cosine, alpha. So this cosine function is going to be 1 at alpha because the cosine function starts here. So at alpha and at 2 pi plus alpha or 360 plus alpha, this is going to take the maximum value at r and the minimum value at negative r. Okay, I hope this is crystal clear. Now, let's say I give you another question, 6 cos theta plus 8 sine theta, and I'm asking you to find its greatest value. Pause the video, find it yourselves. Okay, I hope that you guys have found it by now. Students should immediately think that r is equal to nothing but square root of 6 square and 8 square, which is 100, which is nothing but 10. So r is 10 and nothing more. So I can rewrite it as either. Now see how I can rewrite this as. So this can either be rewritten as r cos theta minus alpha, which is tan inverse of 8 over 6. So tan inverse of 4 over 3 is going to be whatever. So let me say that this is p. So this can be either rewritten as tan cos theta minus p, or you can rewrite this as 8 sine theta plus 6 cos theta, and again r is going to stay the same. So tan sine theta plus alpha, and alpha is going to be now tan inverse of 6 over 8, which is 3 over 4. Okay, so let me call this q. So theta plus q. So you can rewrite the same function because this function and this function are one and the same thing. So you can rewrite this as either tan cos theta minus p, which is where p is tan inverse of 4 over 3, or 10 times sine of theta plus q, where q was tan inverse of 3 over 4. Okay, now I hope this example is clear, because this is all that there is, except for when you bring this down in the denominator, you bring this r cos theta minus alpha down in the denominator and then try to find the maximum minimum values, and sometimes there's a constant attached to it as well for vertical shift. Okay, we will come to that in a bit. Now if I ask you to find the range of 5 cos theta plus 12 sine theta, 5 cos theta plus 12 sine theta, so this is nothing but 13 cos theta minus tan inverse of 12 over 5, whatever that is. Okay, tan inverse of 12 over 5, yeah, or let me write down 2.4. So tan inverse of 2.4 in degrees, whatever that is. So you write that down, put it here, and so the maximum value is at 13 and the minimum is at minus 13. So this is exactly how Cambridge phrases many questions. Now, when does the maximum occur? Now, when does this maximum occur? The cosine, the maximum, let's say that tan inverse of 2.4 occurs at, I don't know, 53.13. Let me, where's my calculator? So tan 2.4. Wait a second. So it is 67.38. Okay. Now 13 times cosine of theta minus 67.38. Now so this graph has shifted 67 degrees to the right and started there, right? So it's ending at 360 plus 67, starting at 67.38, whatever. So the maximum, this maximum value 13 and the minimum value minus 13 occurs. So the maximum value occurs at 67.38 and 360 plus 67, whatever that is, 427.38, I don't know, right? And the minimum occurs at 180 plus 67.38. Okay, so it's as simple as that, nothing fancy here. Now this is something I want you guys to notice. Cambridge almost never asks you to find R. Instead, it asks find the greatest possible value or find the range or hence solve. The rewriting is only step one. The marks come afterwards. Okay. So the common mistakes that there are in this chapter is that students write maximum is equal to 1 instead of R. So the maximum value is not the maximum value of the cosine function, but the multiple of this cosine function, which is 13 times this. So if the maximum value of the cosine function is 1, then the maximum value of 13 times cosine function is going to be 13. Okay, and similarly for minus 13. Mistake number 2 is that the students forget that cosine can be negative. Therefore, minimum is going to be negative 4, negative r, because this takes a minimum value. This function takes a minimum value at minus 1. So when you multiply minus 1 with 13, you get what? You get a minus 13, right? So the minimum value occurs, the minimum value is at minus r and occurs at whatever value, which I just taught you how to find out, right? Now students correctly calculate r but use the wrong alpha because they ignored the sign of one coefficient. Always verify by expanding. I taught you that above in this lecture. Now a mini Cambridge question. If you're given, suppose you're given 3 cos theta plus 4 sine theta equals to k. Find the values of k for which solutions exist. So first of all, I can rewrite this as 5 cos theta minus tan inverse of 4 upon 3. Now tan inverse of 4 upon 3, let me just do it quickly. So that is 53.13. Okay, of course. So this is 53.13 is equal to k. Now, how do you see this graph? So this graph starts at 53.13, right? And completes one cycle at 360 plus 53, which is 413.13. Okay. Now, they're saying for which the solution exists, which means that at most there is going to be one solution, which is going to be at the minimum. I'll just show you. that the solution is going to be here, where this k is just y is equal to k is tangential, or there are two solutions or more, right? Because this curve is going to come here, is going to go there, because it's a perpetual wave, right? So the maximum point is at 5, the minimum point is at -5. This is the origin, right? So, and this is the theta axis, this is, let's say, y, the dependent variable axis. So k has to be between 5 and -5. Okay, that's it. It all it takes, so because I was trying to explain it to you, otherwise all it takes is actually just 15 seconds. Now this is where top students separate themselves. Average students finish rewriting and stop. Top students immediately ask, now what information does this new form give me? Maximum, minimum, range, solutions. That's exactly how Cambridge expects you to think. Now we have learned how to derive the auxiliary angle formula, r cos theta minus alpha or r sin theta plus alpha, and how to calculate r and alpha, and how to write expressions in the required form, and how to use that form to find maximum and minimum values. Let's finish today's lecture exactly the way Cambridge would, with a full P3 question that combines everything we have learned. Then I'll show you why Friday's trigonometric equations lecture is the natural next step, and how all three trigonometry lectures fit together. Okay, now that so far we have learned everything the examiner expects before asking a full P3 questions. We have learned where this auxiliary angle formula comes from. We have derived r is equal to square root of a square plus b square, and how alpha is the tan inverse of b upon a, where b is the coefficient of the other ratio. If we are finding cos, so it's the coefficient of sine. If you are finding sine, then it's the coefficient of cos, right? And finally, how to find maximum and minimum values. So now, if I ask you a question, if I ask you that, let's say that fx is, okay, let's do it on a new page. Let's say fx is equal to 5 cos x minus 6 sin x, where x belongs to all real numbers. I can see that this is this should be in pi. So part A is asking us to express it in the form r cos x plus alpha, right? And y plus, because there is a minus here, right? So it is ought to be a plus. Okay, now it's very easy. So r is going to be the square root of this and this, and the squares of this, the sum of the squares of 5 and 6. So 25 plus 31 is under root of 61. That's simple. and we are also given that alpha is acute. It lies between 0 and pi by 2. Okay. Of course, it can't be 0 and it can't be pi by 2. So it's a strict inequality. So alpha is going to be equal to tan inverse of 6 upon 5, and put your calculator in the radians mode, and you are going to get 0.876. So this is the final answer. Now, in part B, if you had to solve the equation 5 minus 6 sin x equal to 4. So you first convert this into this root 61 cos x plus 0.876 is equal to 4, divided, and then you solve this entire thing. Okay. And then you are going to have two solutions, because this is positive, this is cos. So in the first quadrant and in the second quadrant, we'll do the solutions in our next lesson on Friday. So I want you to see the architecture of this chapter. Monday, the first lesson, we built the language, we learned identities. Today we learned how to simplify two trigonometric functions into one, fuse the two waves into one. Sorry, I'm having bad hiccups. Sorry. Friday, we'll use that one function to solve complete Cambridge equations. Notice how every lecture depends on the previous one. Nothing is random. So today you learned why Cambridge uses the auxiliary angle method, which is r cos theta minus alpha, why r is equal to square root of a square plus b square, why alpha is the tan inverse of b upon a, How do you convert expressions? How do you find maximum minimum values, the range, the examiner shortcuts? That's an enormous amount of mathematics from one single idea. I leave you with one thought. Students often tell me, sir, I memorized the formula but forgot it in the exam. That tells me one thing: you memorized, but you never understood. When you understand the derivation, you don't actually need to remember very much. Even if you forget, you can rebuild it. That's exactly how mathematicians think, and that's exactly how Cambridge rewards the students. If this lecture genuinely helped you understand the auxiliary angle method, please support the channel. Give this video a thumbs up, subscribe if you haven't already, and most importantly, share it with one friend preparing for Cambridge Math. Someone else might need this explanation as much as you did. If there was any part that you guys did not understand, comment about it in the comment section. For quick revision, examiner tricks, challenge questions, and save worthy posts and carousels, etc., you can follow me on our Instagram. It goes by the name of Easy, EASY Taleem, TALEEM, or reach out to me on WhatsApp for structured support, +92 32930288485. That's where we post content almost every day to keep your math fresh between lectures. So if you're preparing for October, November 26, if you're resetting for your P3, or if you're preparing for May, June 27 from start, if you just graduated from AS and you want structured preparation, including live interaction classes, recorded lecture library, worksheets, topic tests, possible practice, doubt solving, performance tracking, 24/7 support on WhatsApp, you can reach out to me on my WhatsApp. Even if you're not enrolled, keep following this free lecture series. Every lecture remains on YouTube, so you can revise whenever you need. On Friday, we complete the entire A2 trigonometry chapter. We'll study trigonometric equations. We'll combine identities, double angle formulae, compound angle formulae, and today's Rcos, theta minus alpha method to solve full Cambridge P3 questions. By the end of this week, you'll have completed one of the biggest and most heavily tested chapters in P3. So until Friday, keep practicing. Don't memorize mathematics. Understand it, because once you understand it, the exam becomes much calmer. Take care, and I'll see you in the final trigonometry lecture. Allah Hafiz.